Define identity matrix as I sub 2 equals 1, 0, and 0, 1. Each column, the first column, 1, 0, is one of your standard basis matrices. E2, the second column, it just means you have 0 and 1. So if it's the subscript 2, 1 in the second position, subscript 1, 1 in the first position. I2, which is the notation for identity matrix, whatever number here, that's how many ones you'll have in a square matrix on the main diagonal. All other entries will be 0. Example, suppose T3 is a linear transformation from R2 into R3 such that the transformation of E1 is equal to this 3 by 1 vector, and the transformation of E2 becomes this vector. These are the images of E1 and E2. With no additional information, find a formula for the image of an arbitrary x instead of E1 or E2, just any x in R2. All right, so let's take vector x, and we'll have the first and second entries. X1 times 1, 0 plus x2 times 0, 1. Again, if you were to multiply, then add, you would get x1, x2 back. But we're splitting it up into x1, x2 with the standard basis matrices. This is equal to x1, e1 plus x2, e2. Since t is a linear transformation, that property holds. Okay, so the transformation of x, and from the video right before this one, we looked at some properties of linear transformations. One of them was being able to take multiplication. If you had a scalar or a weight, you could either do the transformation of both of these, or you can take that scalar out and just do the scalar times the transformation of the vector itself. We also preserved addition. So scalar multiplication and addition are preserved with a linear transformation. So x2 is the times the transformation of e2. Long story short, now we can substitute. We were given the transformation of e1, the transformation of e2, and now we'll multiply x1 and x2 into these numbers. Note 5, negative 7, and 2. Those all belong to x1 or multiplied with it. Negative 3, 8, and 0. Negative 3, 8, and 0, those are attached to x2, which gives you matrix A and the arbitrary vector x. And that's how you would define your transformation. Theorem. Let T be the linear transformation from Rn to Rm. Then there exists a unique matrix A such that the transformation of any vector is equal to matrix A times that vector for all x in Rn, Rn being your domain. In fact, A is the matrix M by N whose jth column is the vector T of Ej, the transformation of that vector. Ej is the jth column of the identity matrix. And we looked at the definition of both of those on the previous slide. Matrix A will be the linear transformation of all of those vectors depending on size. A is called the standard matrix for the linear transformation of T. Standard matrix for the linear transformation of T. Example, find a standard matrix A for the dilation transformation Tx equals 3 times x. And in a previous video, we also looked at having a scalar multiplication of 3. First, let's transform each basis matrix. Now, all the x's are in R2, so our standard basis matrices only need 2 entries. E1, E2. If you triple them both, then you get 3, 0, and 0, 3. Put those columns in order. Transformation of E1, and then transformation of E2. A mapping is said to be onto if each B in the codomain is the image of at least one X in Rn. Alright, so notice the transformation is Rn, that's the domain, Rm is the codomain. If you multiply through and you take all X's from the domain and you put them through the linear transformation, but their images only come out to a certain part of the codomain, like say this part's the range, then that transformation is not onto, because there are some vectors in the codomain that aren't covered by that transformation. If it's onto, then every vector in the domain will completely cover the space over here in the codomain. Onto covers them all, not onto covers some but not all. Definition: a mapping T from Rn to Rm is said to be one-to-one if each B in Rm, so everything in the codomain, is the image of at most one X in Rn. Now let's look at a diagram to try to make some sense of this. I just randomly picked 3 X's from the domain. Let T be their transformation. Those first 2 vectors map to the same vector in the codomain, and because it lands in the shade over here, it's actually in the range. Not one-to-one, because you have 2 X's that get transformed to the same image. The third one was fine. It got mapped on a one-on-one basis. Now, an example of one-to-one would be each individual vector in the domain is an image, or gives you all unique images over here, whether they're in the range or just part of the codomain itself. Let A be the standard matrix for T. If matrix A has a pivot in each column, then your transformation is one-to-one. A pivot in each column. Now again, this is not an augmented matrix. This is a coefficient matrix or a standard matrix. But a pivot in each column means the transformation is one-to-one. A pivot in each row, then your transformation is onto. And there are times when you have both. And I think bijection is the word for that, where it's one-to-one and onto. But you can have one or the other, or both. Let T be the linear transformation from R4 to R3, whose standard matrix is a 3 by 4. Note, this is not an augmented matrix. That's what I had mentioned on the previous slide. Augmented would be if you wanted to set this equal to all zeros or just some other 3-entry vector. Question 1, does T map R4 onto R3? Question 2, is T a one-to-one mapping? Okay, so let's take matrix A, and I just recopied it down here. Row reduce. Again, remember, this is not an augmented matrix. When you row reduce, you have a pivot in column 1, column 2, and column 4. So you're missing a pivot in column 3. That means it's not one-to-one, because we're missing a pivot in a column. But it is onto, because every row has a pivot. Theorem, let T be the linear transformation from Rn to Rm. T is one-to-one if and only if Tx equals 0 has only the trivial solution. That goes back to having a pivot in every column, because you can have a specified answer for each entry of your vector. Let A be the standard matrix for T, and then T maps Rn onto Rm if the columns of A span Rm. It's actually easier just to look for pivots in each row for onto, pivot, and in my opinion, and pivots in each column for 1 to 1. T is 1 to 1 if the columns of A are linearly independent. And again, that would be 3 pivots. A pivot in each column, let me rephrase that. Fact, column vectors can be written in rows. This is just a different notation. X, so far we've seen it as this vector notation, but you can also write it as an ordered, what looks like an ordered pair. X1 on top or first, X2 on bottom or second. The transformation of that vector, you can also write it in a row format. So those are a couple of examples. Let the transformation of vector X, which has 2 entries, be equal to these 3 entries. Show that T is a 1-to-1 linear transformation, and then we'll also investigate whether T is onto. Okay, so let's look at the transformation of X. 3x1 plus x2, 5x1 plus 7x2, x1 plus 3x2. Take the coefficients and make that your standard matrix, A, the coefficients. And then here's our arbitrary vector X. Now, we are going to create a homogeneous augmented matrix here. We still have matrix A, which is the coefficients of x1 and x2, and in the last column we're just going to put all zeros. Basically, it's Tx equals 0. All right, so we're going to write that transformation equal to 0 as an augmented matrix and row reduce. We have a pivot in each column, because remember, there's only 2 columns to it, x1 and x2. x1 has a pivot, x2 has a pivot. x2 is equal to 0, x1 is also equal to 0. So X being 0, 0, that's the trivial solution. So you can look at it in 2 ways. The trivial solution tells us that the transformation is 1 to 1. A pivot in each column of A, there was only 2 columns. A pivot in each column also tells us that T is a 1 to 1 linear transformation. Now, because there's a 3rd row but it doesn't have a pivot, since there are not 3 pivot positions in matrix A, T cannot map onto R3. And another way to think of that too is if you just take all matrices of 2 entries, there's no way you're going to cover all vectors of 3 dimensions or 3 entries. As usual, email me with questions or concerns, and I'll be happy to try to help you out. Don't forget to read your e-text. This is the last video for chapter 1 out of the text. It's the longest section. The next series of videos, we're going to move on to chapters 2 and 3. In each one of those chapters, we're only going to cover 3 sections. So that's going to be nice to finally have a break on such a long chapter. But there's 9 sections total in chapter 1. On MyLab Math, on your online homework and test platform, I did break it up into 3 chunks, parts 1, 2, and 3. And then we'll have a test over chapter 1. You'll see everything posted on there with due dates. But anyway, I wanted guys just to head you up and let you know to always ask questions anytime they come up. I check email frequently. And anyway, hope you have a good day. Thank you.